Welcome to this podcast, Semiconductors, the Enablers of Quantum Technology. I am Dr. Sriganesh Rao, member of a research team under the Maitri Grant program of DFAT Australia for developing a roadmap for Australia and India collaboration on semiconductors. I have with me Professor Simon Devitt, who is a professor and the research director of the Centre for Quantum Software and Information at the University of Technology, Sydney. Professor Devitt received his PhD from the University of Melbourne. He has held various research and academic roles at the Cambridge University, Japanese National Institute of Informatics, Okanomizu University, Tokyo, Keio University, Tokyo, Japanese National Labs, Riken, and the Macquarie University, Sydney. He is also currently the co-founder and managing director of a quantum education startup, Egan Systems Private Limited. He is also the co-founder and managing director of H-Bar Quantum Consultants and also director of the Australian Quantum Software Network. He is a visiting chair of excellence in quantum technologies at Aalto University, Finland, and a visiting senior research scientist at Riken, Japan. He is also a member of the Australian National Quantum Advisory Committee. So Professor Devitt has published 145 journal publication and has held 11 patents. He is a fellow of the Australian Institute of Physics and fellow of the Royal Society of New South Wales. Welcome, Professor. It is
Thank
great
you.
to have
It's a
you.
pleasure to be here.
It's a great to have you. In spite of your very busy schedule, you actually taken time off for this podcast. I thank you for that.
Thank you very much.
Uh, could you actually tell us about your journey in the quantum field?
So, yes, I was an undergraduate in physics at Melbourne University in the early 2000s. And when I hit sort of my fourth year honours, as we have it in Australia, just before your PhD, there was a bit of a strange thing about which direction I wanted to go in. Did I want to go to, at the time, it was high energy physics. That was sort of the most popular thing, doing high energy theory and those kind of things. And quantum was very small at the time. And I wasn't smart enough to do high energy. My theoretical physics wasn't quite good enough. So I ended up working for Professor Lloyd Hollenberg, who was a theorist in quantum at Melbourne University. And that's where I sort of got into quantum technologies and quantum information. So it was a bit serendipitous at the end because I think I was a lot better at quantum information than I ever would have been in high energy theory. And certainly back then, there was a lot of work to be done. Quantum technologies hadn't become as popular as it is today. Back in the early to mid 2000s, it was still sort of a niche area of physics. And then over the course of the 2000s and the 2010s, it really turned into a field of its own. Some would argue it's become even bigger than what I originally planned to do, which was high energy theory. So I finished my PhD at the University of Melbourne in late 2007. I then took up a position at the National Institute of Informatics in Tokyo, where I was a postdoc and then an assistant professor for about 7 years. And then I had, after that, for the next 4 or 5 years, varying positions in the Japanese ecosystem, helping to develop their quantum technology industry. And then in 2017, I returned to Australia, took up a position at Macquarie University for a year, and then became a faculty member at the University of Technology, Sydney, where I've been ever since, in order to sort of keep developing the quantum ecosystem in Australia from an academic perspective. But then, as you mentioned, I have several side projects. I founded HBAR Consulting back in 2015 with a colleague of mine from RMIT University in Melbourne. At the time, quantum had just started moving out of the academic space into the industrial space. And we thought that there would be, and we were somewhat right about this, there was a burgeoning industry of people trying to connect sort of academia with the VC community. A lot of venture capitalists were trying to look at investing in quantum, but had really no idea what quantum was. So we sort of filled a little bit of a gap there. And then subsequent to that, yes, I've founded another company that is focused on quantum education and quantum literacy called Eigen Systems with our flagship product Quokka, intending to build quantum literacy and quantum training programs around the world. And one of my other hats is director of a new non-profit in Australia called the Australian Quantum Software Network, which is a collaboration between sort of all the theorists, algorithm development people, and software engineers working on various aspects of quantum, whether it's communications, computing, or sensing.
Wow. I'm sure it was a very great journey, and quantum being the future, it must have been exciting for you in this.
It has been. It's been really interesting to see how the field has evolved, especially in the last 10 or so years. We've gone definitely from a very academically focused industry to what is now an extremely highly valued and highly capitalized industrial sector. I suppose if you look at the quantum companies that exist across the world, whether it's quantum divisions in big corporates like IBM, Google, Microsoft, to the startups, whether it's the publicly listed startups, whether it's IonQ, Rigetti, D-Wave, and even to the ones that are still private but are very, very well funded by venture capital, whether it's PsiQuantum, Xanadu, some of these other companies, you're talking billions and billions of dollars of investment now coming from the VC community and from governments, whether it's the Americans, the Europeans, the Australians, the Japanese, even the Indians, has really now become a burgeoning industry across a multitude of companies and countries.
Mm-hmm. So when you talk about quantum, we talk about qubits. What are qubits, and what are their role in the quantum technologies?
So qubits are the fundamental unit of information in quantum information in the same way that bits are the fundamental unit of information within classical electronics. So in classical electronics, you have the bit. It's basically a 0 or 1, an on or an off. And from that, you can build up what we call universal models of computation. So if I have the ability to define a bit, a 0 or a 1, and I have some certain operations I can do on that bit, you talk about AND gates, OR gates, these kind of basic logic gates, you can build up computational primitives. You can do things from basic arithmetic, adding two numbers together, to ultimately what we're doing right now, which is, we've got a video conference between Australia and India, but it's all still fundamentally based on the concept of a bit, a thing that's on or off, 0 or 1, and how you process that information. A qubit is the quantum version of that. So a qubit is a quantum bit. Qubit, that's where the name comes from. Now, in quantum, a qubit is a slightly different thing. It has what we call a state space, or a position in which it can store information that goes beyond just 0 or 1. It can go 0, it can go 1, it can go to any combination of 0 and 1. And that opens up a different model of computation that's just fundamentally different than what we see with classical. So when you build up a classical model of computation, whether it's a CPU or a GPU, you're hearkening back to very early developments in classical computer science about what the rules of the game are. You think Alan Turing, you think John von Neumann, these kind of people that sort of said, these are the rules that you play by, and these are the kind of things we can calculate. There's quantum equivalents of all of this that based on the qubit. And when you have a qubit, when you have, the kind of information that quantum mechanics allows you to store, there's just a different set of rules. And what we've found out over the last 30 or 40 years is that when you have this new toolkit, when you have this new set of rules, there are certain problems that you can solve in a fundamentally different way than you can solve classically. So algorithms become more efficient. They require less steps to get to an answer than they would on the classical, bit, Turing model kind of computation. So to sort of explain what a qubit is and how quantum information works requires you to dive deeply into sort of the nature of quantum mechanics and philosophically, what does quantum mechanics mean and all this kind of stuff. But the way to think about it is we've just got a different computational toolbox where certain problems become more efficient. When you start thinking about, if I've got these objects called qubits that obey these rules that are different from bits which obey these rules. And once you open up that box, there are certain things you can do more efficiently with quantum computers than you can with classical computers.
Okay. What is the role of semiconductors in quantum technologies?
So one of the things that a lot of quantum hardware companies try to do is they certainly present themselves or market themselves as being what they call CMOS compatible
Okay.
or semiconductor compatible. And what they mean by that is the hardware manufacturing that they require to produce quantum computers or large arrays of qubits can
Mhm.
sort of be piggybacked off the classical infrastructure that we already use for developing silicon semiconductors. So obviously, companies and countries around the world have invested trillions and trillions of dollars
Mhm.
into high-end semiconductor manufacturing. Think of the Taiwanese, think of the Koreans, the Japanese, even the Indians to a certain extent. There's a lot of money that's gone into developing fabrication facilities and developing infrastructure that allows you to do high-end chip manufacturing where you're, creating little transistors on silicon wafers at very, very fine resolution. So, you talk about semiconductor manufacturing at the 14 nanometer scale or the 5 nanometer scale. This sort of talks about the length scale where we're sort of patterning transistors, which are the fundamental units that we use to create GPUs or CPUs. So when quantum companies talk about the silicon industry, what many of the hardware companies are trying to do is figure out, in a quantum system, can I develop qubits that can leverage that infrastructure? Where manufacturing qubits requires the same kind of infrastructure that you already use to manufacture silicon chips. Now, there's some hardware modalities that do this better than others. So in quantum, it's a bit different than classical. Like people might remember back in the day where you talk about the fight between Intel and PowerPC,
Mhm.
where you've got different kinds of chips. Apple used PowerPC and Windows machines use Intel.
Yeah. Mhm.
But at the end of the day, they were still silicon-based transistors. You still had silicon nanofabrication that built the devices. They were just different architectures. In quantum, we have at least 9 different systems that are completely different from each other. So
Okay.
qubits can be defined as particles of light. Qubits can be defined as the spin of an electron in an atom. It could be
Mhm.
a current running
Mhm.
around a superconducting circuit. It could be the state of a neutral atom in an optical trap. These are very, very different technologies
Mhm.
in terms of their hardware manifestation of a qubit. And what a lot of companies try to do is figure out what kind of way can I build a qubit that allows me to go to tier one semiconductor foundries like TSMC, could be Global Foundries, could be Samsung, and sort of tweak it a little bit and be able to manufacture my qubits. Some systems are better than others to do this. Certainly,
Mhm.
most platforms proclaim that they can do this. But depending on the actual way that you design quantum computers, some are a little bit more amenable to silicon manufacturing than others.
Mhm. And actually, what are the materials, which are used for the quantum technologies?
So
I
again, it
mean,
depends
semi.
on the kind of technology that you're looking at. So you can have a spin-based quantum computer. For example, you've got companies like Silicon Quantum and Dirac here in Australia.
Mhm.
Silicon Quantum uses an approach called phosphorus donors, where you have a silicon lattice. And within that silicon lattice, you remove individual atoms of silicon, you replace them with phosphorus.
Mhm.
And it's the spin state of the nucleus of that phosphorus that's actually your qubit. So you have these little individual phosphorus atoms in an array. They're your individual quantum bits for your quantum computer, and they're buried within a silicon wafer. Dirac is another silicon based company. They do what's called gate defined quantum dots. So these are
Mhm.
artificial atoms that are created by constraining a certain area of your silicon with sort of gates. And within
Mhm.
that, you create an artificial atom where you've got electrons that orbit certain specific energy levels, and you can use that for quantum information processing. These two systems are the most amenable to mass manufacturing in the silicon industry. But you've got other companies. PsiQuantum, for example, uses single particles of light that go through waveguides that are etched within a silicon nitride crystal. So you basically etch in waveguides into this waveguide. You've got single photons that pass through it, and you do quantum gate operations that way. You can have ion trap technology where this leverages silicon manufacturing a little bit less because you literally have copper based electromagnetic traps. and you have a single ion. Could be calcium, could be beryllium, could be ytterbium that sit inside an electromagnetic potential defined by these gate electrodes. And you isolate single atoms, which you then use as qubits. So it very much depends on the kind of technology that you're looking at as to how much it can leverage the semiconductor industry and how much it can actually continue to exploit what has been done in classical semiconductor engineering.
So photonics also has it plays an important part in the quantum computing, right?
It does. There are certain quantum systems that are all photonic. As I said, PsiQuantum and Xanadu are two companies that are pursuing this option. But even companies that don't use photonics to build their qubits is still looking at sort of photonic systems to try and interconnect parts of their computer. So if I've got a little microcomputer of ion-based qubits here, and I've got another one over here, I might want to talk to them using integrated optics, which might be some combination of waveguide-based silicon nanophotonics and optic fiber technology to get one unit to talk to another unit. So companies like Quantinuum, IonQ, when they talk about scaling, how they're going to create a quantum computer which could contain millions, if not billions of qubits, how do they scale their systems to that level? And they talk about distributed models where you might use silicon nanophotonics, you might use some kind of optical coupling technology to get one part of the computer to talk to another part of the computer.
What are the roles of silicon and gallium nitride in the quantum sensing?
In quantum sensing, it's less clear. So quantum sensing is an interesting topic in and of itself as to what's being developed versus what quantum sensing really is. And I've had discussions and arguments with people in the quantum industry about this. So remember that quantum technology is not new. Quantum technology is 100 years old. So the laser is quantum technology. MRI machines, that's quantum technology. The transistor, everything in your computer is quantum technology. None of these technologies would not work if it wasn't for quantum mechanics. What we're talking about with quantum technologies today is second generation quantum technology. So quantum computing is different from computing. Quantum communications is different from communications. There's something new that you get by exploiting the quantum mechanical behavior of individual particles. Quantum sensing is an interesting topic because what I would call, I don't agree with this characterization, but certainly it's the way that people are sort of moving forward in this. What is called quantum sensing right now is, in my opinion, not quantum sensing. So quantum sensing, as you see many companies developing, so this could be magnetometry, this could be gravitational sensors, a whole bunch of different things depending on the application. What people are focusing on right now is sensors that are smaller, easier to package, less power hungry, what we call SWAP, size, weight, and power. So they're smaller, they weigh less, and they consume less power. But the sensing that they do is not, in my opinion, intrinsically quantum mechanical. They're just better at sensing certain things. So you can have an atom that is very, very sensitive to magnetic field fluctuations, and you can use that as a sensor. But that's just a better sensor because magnetic field sensors have been around for a long time. They're called Hall effect sensors. They are based on quantum mechanics in the same way that a transistor is based on quantum mechanics. Where quantum sensing gets really interesting is when you have entangled particles that do the sensing. And it's called, in sensing, it's called hitting the shot noise limit. So how many measurements do I have to make of like a magnetic field or a gravitational field to get a good resolution on the value of that magnetic field or gravitational field? The way it scales is 1 over the square root of the number of samples that I take. What's called the shot noise limit. Quantum mechanically, you can beat this limit. You can go from 1 over root n to 1 on n. So you can get a better efficiency. But this requires your sensors to be entangled quantum mechanically. That's not the sensors that people are building right now. The first generation of quantum sensors do not beat the shot noise limit. They are just sensors that happen to be smaller, weigh less, and require less power. Now, to the extent at which silicon manufacturing plays a part in this, it depends on the sensor. It depends on what it's trying to sense, what is the quantum mechanical system that's being used to sense that property, and how it's packaged. So, for example, most magnetic field sensors use what's called nitrogen vacancies in diamond. So you have a carbon lattice, which is diamond, and you replace one of the carbon atoms with a nitrogen atom. That's your qubit, and that's very good for magnetic field sensing. That doesn't require silicon at all.
Okay.
There might be control structures, anything like that, but the sensor itself is effectively a diamond-based sensor. And there's other systems like this. So within the sensing community, there's not a huge amount of silicon manufacturing going on right now because they're not the primary systems people are using for quantum sensing. And that's aside from what I just said before. And again, I am in a minority in this with my opinion, that they're not true quantum sensors, because to reach that realm of quantum sensing, I need to exploit entanglement, which these sensors don't do.
Okay. So overall, what could be the role of the semiconductors in quantum computing?
Again, most systems do use semiconductors to a certain extent, but some systems more than most. So if you look at superconductors, if you look at ion traps, there's a certain level of semiconductor manufacturing going on with those systems. If you look at spin systems, whether it's the kind of computers that Dirac is selling, HRL Labs, silicon quantum computing, there's a lot of silicon infrastructure going on in those systems. Now, they're not as advanced. So the best systems that exist right now are either superconductors or ion trap quantum computers. They're the best ones that exist today. But in the future, that might not be the case. Certainly the argument is being made by these companies that because we are compatible with CMOS manufacturing in the silicon industry, we can potentially scale to millions, if not billions of qubits in the future. Whereas superconductors, ion traps, some of these other systems have a harder time getting to that scaling. So certainly a lot of these companies are trying to figure out ways where they can exploit the silicon manufacturing industry as best they can. But there are some systems that you can do this easier than others. As I said, ion traps, superconductors, you can exploit it a little bit. There are some stuff you can do with silicon, but fundamentally the qubits are not silicon-based. Whereas spin systems, they're silicon-based or germanium-based. They're compatible with CMOS-type manufacturing. And even photonics, something like Xanadu or PsiQuantum, they're still manufacturing in the silicon regime. So it really just depends on what system happens to scale over the next 5, 10, 20 years. There's certainly arguments to be made that the systems that are less advanced today will leapfrog these other systems over the next 10 years and be able to go to scale much easier because they can leverage what's going on with TSMC, with Samsung, with these other tier 1 foundries.
Yeah. What is the motivation for you to start your education startup, Eigen Systems?
So this sort of came out of the work that we were doing at UTS with trying to, educate computer science students in quantum. And what we've seen is there's a couple of reasons for this. The quantum industry is very highly capitalized, but it's very there's a massive talent shortage within the industry. You've got a lot of companies who are raising a lot of capital, whether it's the VC market or the public markets. They're trying to grow their companies, and there's just not many people out there because we've sort of gone very, very steep in sort of how the quantum industry has grown. We've gone from a very academically focused industry, and then it's sort of this cliff face, and suddenly everyone's got a lot of money and there's a lot of companies that are hiring people actively. So in order to get people who have PhDs, have masters in this field who can go into that industry, the beginning of the pipeline has to be good. You need to feed a lot of people in at the high school level going into university with quantum in mind. If for every one person who comes out with a master's or a PhD who can enter the quantum ecosystem, you have to provide 100 to 1,000 people on the other side. Because, people drop out, people decide to change their careers, people decide that they don't want to be a scientist. You have attrition as you move through that system. So that's one of the reasons that we've tried to do this with Quokka, is to start building that earlier pipeline where you're talking to students who are in junior high school and high school who are going to move into university. The second reason we've done Quokka is quantum mechanics over the last 100 years has gained a bit of a reputation. And you see it when you hear quotes like, there's very famous quotes from people like Feynman, from people like Niels Bohr, where it's like, if you think you understand quantum mechanics, you don't understand quantum mechanics. And there's a reputation that quantum mechanics has been, nobody understands it. You've got to be a genius to work with it. There's a barrier there that has grown up over the last 100 years since the theory was first developed that provides a barrier for students because they look at this and they go, I don't think I'm smart enough to understand it. So I'm not going to pursue it. I'm going to learn how to code, or I'm going to learn do chemistry or something else. Even though quantum mechanics is not something that's very, very hard to get your head around. Yes, you've got to be good at maths and you've got to sort of understand linear algebra and stuff like that. But ultimately, quantum mechanics is not overly complicated. Where it starts getting tricky is when you want to have philosophical arguments as to the nature of reality with quantum mechanics and general relativity. But in terms of a workable theory where you can get into this industry, it's not particularly difficult. And so what we're trying to do with Quokka is try to introduce students in a very young age and try to demystify it a little bit and say, okay, you don't have to think of yourself as a genius to get involved with quantum. So there's that part of it. And secondly, there is a bit of a media blitz when it comes to quantum. So the Marvel universe deals with quantum all the time. Ant-Man and Quantumania and Captain America and Thor. This again provides a misconception as to what quantum mechanics actually is. And unfortunately, this kind of exposure in popular media is usually what most people think about when they think about quantum. And not only is it scientifically inaccurate, it is completely divorced from the reality of the kind of technology we're building or what the theory fundamentally says about the nature of reality. So trying to introduce this stuff to students at a young age through Quokka and the educational offerings that we do through Eigen Systems is, again, trying to ground people in the reality of quantum, teach them that you don't have to be a genius to understand how quantum computing works or how quantum technologies work, and fundamentally try to either get them comfortable with this technology, because let's be frank, in the next 50 or 60 years, this technology is going to enter into the general population in the same way that digital technology entered the general population in the 1980s and the 1990s. So it's not just about people who want to be a quantum physicist working for a quantum company. In 5, 10, 20 years, you're going to start seeing products on the market that are fundamentally quantum mechanical systems. Whether it's quantum computing systems, quantum communication systems, quantum sensors, these things are going to become part of the general technology landscape that individuals are going to use in the same way that they currently use iPhones, smartwatches, all the other devices that we use on a daily basis. So we need to sort of demystify this for the general population and make sure that they're comfortable with what this technology does and how it enables their lives. So trying to bridge that gap and say, okay, you don't have to be a genius and this stuff's coming. You're going to be exposed to this kind of stuff as you're moving forward. Might not be your generation, it might be your children, it might be your grandchildren. But in the same way that everyone holds a computer in their pocket right now, whether it's an iPhone or an iPad, by the end of this century, everyone's going to be holding something quantum in their pocket. Could be a quantum computing device, could be a quantum communication device. Entanglement is going to be a word that is like electricity, and people have to understand what it is.
Okay. You mentioned your product name in a Quokka. What is the significance of this name? Why this name?
So I have a Quokka here. So this is our Quokka device. This is your own personal quantum computer. This is a 30-qubit quantum computing system that is designed to operate exactly like a real quantum computer from IBM, but it only costs a couple of $100.
Wow.
Whereas the real systems cost you tens of millions of dollars. These systems are designed to function as an educational device and teach you exactly how to program a quantum computer so that you can program the real ones if you get access to it or start working for these kind of companies. Quokka there was two reasons we gave it this name. The first is quokka is a very relatable indigenous animal in Australia.
Wow.
I
Okay.
don't know if you can see the logo here. That's
Okay.
kind of what a quokka looks like. It's a
Okay.
cute little marsupial. It's about this big.
Mhm.
It's related to kangaroos. It's related to other marsupials in Australia.
Okay.
And they're mostly populating an island off the west coast of Australia called Rottnest Island. They're very cute. Um, if
Mhm.
you go to Rottnest Island, you can go take photos with them. They don't have any natural predators, so they're very, very friendly.
Wow.
Um,
Interesting.
so, of course, for an Australian company, we're going to name something after an Australian animal. But the second thing is quokka. The first two letters are QU. And most of the time in the quantum computing industry,
It always starts
companies
with
and
you. Yeah.
yeah, products and companies are often there's Q somewhere, there's U somewhere. They often take a word and they misspell it or they come up with some weird word. Whereas quokka, it was there. It's got QU in the name. It's an Australian marsupial. We
Mhm.
didn't have to do anything. It's like, this is a perfect character. This is what we want. We want to target students. We want to target young people. So, as usual, put a nice little cute face to it, introduce people this way. And it happens to be an animal that already has QU in the name. We don't have to misspell it. We don't have to mispronounce it.
Okay. And of course, this product would be based on semiconductor chips. Um, so did you design this chips, which has gone into the product?
No. So, in this particular case, Quokka is built out of off the shelf components.
All right. Okay.
So it's an emulator. What it does is it mimics the behavior of a real quantum computer. So
Okay.
it's an unscalable method of quantum computing. So we do 30
Okay.
qubits.
Mhm.
Quokka will never do more than 30 qubits ever. There
Okay.
won't be any upgrades. There won't be any, Quokka
Mhm.
version 2. You'll do 30 qubits. That's as much as you'll ever do. But that's enough for education at the moment. And in fact, it's more than enough compared to the actual real systems that exist because
Mhm.
our qubits are perfect. There's no errors. There's no noise. Whereas you can buy a real quantum computing system, might contain 20, 25 qubits from various companies around the world, but they're noisy. They don't work all the time. But it's based on standard silicon semiconductor chipsets. We buy them off the shelf. We have our own code base that emulates the behavior of a quantum computer. That's how we can market it as a cheap, hands-on device for students to have their own quantum computer. They can run their own quantum jobs. They can learn how to program these machines. And our ultimate goal with Quokka is to try to get students to start developing their own quantum programs, their own quantum languages, try to take that next step within the quantum industry where it's like, I know how to run these systems. I know how to program these systems. So can I come up with, can I be the Bill Gates of quantum? Can I be the Steve Jobs of quantum? Where I'm going to build the operating systems and the development environments for the future real quantum computing systems that might take another 5, 10, 20 years to actually realize.
Yeah, it looks very handy, for the students, easily carried in their pockets. And I'm sure, I think it'll be wonderful for the quantum education which you are planning.
Yeah, and it's
Speaking about
designed to
other
be
quantum,
cheap, accessible,
okay,
portable. It works like a Fitbit or a Chromecast. You just onboard it to your Wi-Fi network. You have your
okay,
own quantum computer in the cloud. You can do whatever you want with it.
okay. What are the quantum initiatives in Australia? Because we hear a lot about quantum in Australia. What are the initiatives?
So quantum in Australia has had a long history. The government started funding quantum development, and
Mhm.
as depending on how you look at it, as far back as the 80s.
Mhm.
Certainly, the first centres that were funded in Australia started in the late 1990s. We had special research centres funded by the government that turned into centres of excellence. The Australian quantum industry has been very strong internationally for the last 20 or 30 years. We do have a national strategy that was released, I believe, in 2023 or 2024,
Mhm.
where the government had decided that quantum was going to be a major scientific initiative within the country. And we've got a variety of different, grant programs. We've invested $1 billion in PsiQuantum, who is standing up a photonic quantum computer ostensibly by the end of this decade, up in Brisbane. And whether or not you're talking about it from a research and development perspective through the universities and the academic sector, or you're talking about it from the more industry focused, startups, large corporates who might happen to be doing quantum, there's various mechanisms within the Australian industry for these entities to get funding and for these entities to start developing their products. We've got several hardware companies in Australia. I've mentioned a couple of them: Silicon Quantum Computing, Dirac, Quantum Brilliance. Some software companies like Q Control, sensing companies like Detect, Nomad Atomics. So with respect to sort of the size and the scale of the Australian economy, we're well represented around the world, primarily because we got into this business very, very early. So Australia's been doing quantum for a good 30 to 40 years. Whether or not we're going to be able to keep up with the massive amount of investment that's happening in countries like Japan, India, the United States, Europe, we're still a smaller economy. To what extent we're going to be dominant players in the future is still remains to be seen. What part of the supply chain we're going to be a part of is still unclear. Certainly, many of these nations, India included, are spending billions of dollars in national strategies. We haven't done that yet from a government perspective. And to what extent we're going to keep up with larger economies that are pushing very, very hard for quantum technologies in the next 10 or 15 years, that still remains to be seen.
Yeah, quantum technologies are often discussed alongside with semiconductors as a future-defining field. India has embarked on a domestic journey, which is called as the India Semiconductor Mission, by giving huge incentives for fabulous chip designs, setting up of semiconductor fabs, OSAT, ATMP, etc. And also, India also has an ambitious program called National Quantum Mission, which is centered around advancing various key areas of the quantum technology, including development of quantum computers, secure quantum communication networks, sensing, etc. So, with these initiatives in India, what are your thoughts on Australia-India collaboration in quantum technologies and semiconductors?
Well, certainly there's a big push in Australia to service the Quad. So the Australian government certainly looks at the Quad alliance between Australia, India, Japan, and the United States as a big focal point when it comes to both quantum and semiconductor development. So politically, there is the will. And certainly with our partnerships with India and Japan, there certainly seems to be a lot of touch points and a lot of collaborative points between the three economies. How the United States fits into this is still a bit unclear. The United States is clearly competing with efforts in China. They're competing with efforts in Europe, how much they're brought into it. But certainly from the Australian perspective, the Quad is where they want to hit. And as to how much Indian-Australian collaborations can service both the semiconducting and the quantum industries as we move forward. So there's certainly the will on the Australian side, and I believe that's true on the Indian side and the Japanese side. How much that sort of boils down to, on the ground funding and on the ground incentives for people to start building out the quantum industry in these three countries still remains to be seen. We have to figure out how to do bilateral and trilateral relationships a little bit better. Certainly money flow is a bit of an issue. The Japanese system, for example, very rarely sort of lets Japanese money out of Japan to go fund other things. And the same is true for most other countries as well. So how these collaborations sort of tie together, whether you're looking at the semiconductor industry in India as being sort of a leapfrog to the quantum industry, again, how this develops in the next 5 or 10 years, to me, is a little bit unclear. But certainly the motivation from the Australian government, especially around the Quadrilateral Alliance, is very, very strong. They want to do things with India. They want to do things with Japan. And obviously, they want to do things with the US.
And I'm sure with the free trade agreement between Australia and India now, which is called as the Economic Cooperation Trade Agreement, all this can become a reality now going forward.
Yes, definitely. And I mean, with the National Quantum Mission in India, you guys are starting to be very much more serious about quantum. There's certainly huge interest in India to keep going. This is why our engagement with Quokka has been so successful and so fruitful in India so far. And being able to produce more domestic talent in India and build that domestic industry in quantum is going to be so important for India moving forward. And certainly Australia will enthusiastically partner where it can.
Okay. Yeah, it's been great to have you on this podcast, and so thanks for your time and your valuable thoughts in this area. So thank you once again.
Thank you, Ron. Thank you very much. It was a pleasure.
Thank you. It's a pleasure. Thank you.
Thank you.